Welcome to our chemistry video project. Today we're doing an experiment to melt 3 ice cubes in hot chocolate or coffee. I'm Tom, this is Jance, and our video editor is Jenny. Today we are going to go over some of the steps in the equation, how much energy it would take to melt the ice, so we can find the final temperature of the ice and the water. So some of the equations and principles we have here is this equation right here, Q, which is the heat, equals NC delta T. N is the amount of substance that we have, such as moles or grams, or C is our heat capacity, or how much can this element or this substance absorb heat. What's the rate of it? And our delta T is a change in temperature. So that's one way we're going to use to find how much energy it took for the heat. This Q equals amount times delta H, Q being the amount of heat again, the amount being the amount, of course, and the delta H is our enthalpy change, how much enthalpy it has. So we have here some constants for the ice and the water. This is the specific heat. Our specific heat of ice is 37.6 joules per moles degree Celsius. Joules is an amount of energy used, whereas moles is an amount of substance, like amount of weight. Water, 75.3 joules per moles degree Celsius, is the specific heat of water, liquid water. And our enthalpy of fusion, 6.02 joules or kilojoules per mole. That's how much energy it takes to melt the ice. So our C for this is also liquid water, a specific heat for liquid water, 4.184 joules per grams degree Celsius. So it's similar to this one, except for instead of using moles, we use the grams. And then this is some of the information it gives us in the problem, how much water and ice we have. We have 375 milliliters of coffee, or water. We're assuming the same density as water, so it's going to be 375 grams of coffee set at 90 degrees Celsius. Whereas we have 135 grams of ice set at -4 degrees Celsius.
Awesome. Thank you, Tom. So today, like you said before, what we're doing is putting 3 ice cubes of 45 grams into a 375 milliliter container of coffee. And what we're trying to do is find the thermal equilibrium, or the ending temperature. Okay? And what we will be discussing today, the principles, will be the law of conservation of energy. So the energy is never created or destroyed, it is always transferred. Another principle that we will be discussing is thermal equilibrium. For example, the hot coffee is 90 degrees Celsius, and the ice is at -4 degrees Celsius. We're going to find out what temperature at which they will meet at. How we would do that today is we're going to find out how much energy it will take for the ice, which is at -4 degrees Celsius, to rise to 0 degrees Celsius, at which it's going to need to go through fusion, in which the ice is going to have to turn into water. And then when it turns into water, we're going to see at what temperature the coffee and the ice will meet at, which is thermal equilibrium. All right, so now we're going through the steps in order to get the ice at -4 degrees Celsius to find the thermal equilibrium. So now for step 1, what we're trying to do is we're going to get the ice to the melting point. How we do that is we find how many grams of the ice cube that we have. So if every ice cube is 45 grams, and we have 3 ice cubes, we get 135 grams. Now we want to convert that to moles. So we get the total number of grams, 135 grams, and we divide that by the atomic mass of water, which is H2O. So that'd be 2 hydrogens plus oxygen, which is roughly 1 per hydrogen, so that'd be 2, plus 16 for every oxygen. So that equals out to 18.02. So 135 grams divided by 18.02 gives you 7.492 moles. Okay, and then from this we plug this into the equation of Q equals NC delta T. So we have 7.492 moles times by the constant that we have over here for ice, the enthalpy of ice, which is 37.6 joules moles degree Celsius, We times that by the change in temperature. And this is the final minus the initial. And our final, what we want, is 0 degrees Celsius. Okay? And our initial is -4 degrees Celsius. And we solve this, we actually get 4. So then we multiply all this out, and we end up with 1,126.75 joules. So this is the amount of energy in joules it takes to raise -4 degrees Celsius of ice to 0 degrees Celsius of ice.
Right, so now it's at 0 degrees Celsius, but it's still ice. So we need to melt the ice, we need to make the ice water. So that's our next step, is to melt the ice. So we have this number here, our 7.492 moles of ice, which we got by dividing it by the atomic number of water. So 7.492 times our enthalpy, which is we get from this equation right up here, the amount of heat equals the amount of the substance that we have times our enthalpy. And our enthalpy of fusion is 6.02 kilojoules per mole. So we're going to plug that number in right here, and we have our amount, our 7.492 moles times our 6.02 kilojoules per mole equals 45.102 kilojoules. So now we convert kilojoules into joules. Kilo is 1,000, so we have 1,000 kilojoules per every 1,000 joules per every kilojoule. So that gives us 45,102 joules. We add them two together, and we get 46,228.8 joules. So now, where we're at in the whole map of things, so we took the ice, we brought it up to 0 degrees Celsius, and now we've melted it into liquid water. And that's how much energy it took.
Alright, now this brings us to step 3, which we're going to cool the coffee using the energy it took to raise 4 degrees Celsius of ice to 0 degrees Celsius, and then through fusion to get the number of joules total. So we're going to use this number here to find out the temperature change in coffee from 9 degrees Celsius to whatever amount we find out. But first we need to convert the number of grams to moles. So over here we have the assumption that 375 milliliters equals to 375 grams of coffee. So here, and then we divide it by the atomic mass, like we discussed earlier, of H2O, and we get 20.81 moles of coffee. And now what we want to do is we want to find delta T, the change in temperature. In order to do that, we solve for delta T in the equation Q equals NC delta T. What we get is delta T is equal to Q over NC. And so now we plug in all the numbers that we have. We first have 20.81 moles, then we have a constant, which is 75.3 joules of moles times Celsius, which is the enthalpy of water, and then we plug in the number of joules right here. Because of the law of conservation of energy, energy is never created or destroyed, but the energy from coffee was actually transferred to ice, which rose the temperature to 0 degrees. So now we plug it in here, and the answer we get is 29.502 degrees Celsius. Now we subtract that from 9 degrees Celsius, in which we find out that it's 60.498 degrees Celsius. So to sum all that up, in conclusion, we found out that the energy it took to raise -4 degrees Celsius to 0 degrees Celsius, and then through fusion it was 46,228.8 joules. We then used that in order to find out how much energy the coffee gave off to the ice to raise that temperature to 0. And then we found out that after that gave off the energy, the temperature of the coffee is now 60.498 degrees Celsius.
All right, so at this point, we have some liquid water at 0 degrees Celsius, and we have our warmer water, that's towards the coffee, at 60.498 degrees Celsius. But those two temperatures are those two masses are going to have a temperature change as well. So now we're going to find out what will be the thermal equilibrium, or the temperature when the temperature change stops when they both reach the same. So how are we going to do that? We've talked earlier about the law of conservation of energy, about the Q, the energy, equals the negative Q. So that energy has to come from somewhere. So we have our amount, the Q equals NC delta T in this equation equals negative NC delta T, because of the law of conservation of mass, of energy. So we're going to plug some of our numbers in here. We have our ice, we have 135 grams of ice times 4.184 joules per grams degree Celsius. This is our specific heat of water. Instead of using 75.3, because that's moles, we used the 4.184 because it's in grams. So now we're solving for the final temperature. The delta T is final temperature minus the initial temperature. So delta T, or final temperature minus 0, which is our initial temperature of the water. Our next step, or next other side of the equation, is our negative NC delta T, which we have 375 grams of coffee, and the specific heat of water again, minus temperature final, or times the temperature final minus 60.498 degrees Celsius, which is our starting temperature of the coffee. So, doing some algebra here, we're going to combine these two terms together, and we get 564.84 times our delta T. And the same thing on this side, we multiply those two numbers together. We got negative 1,569 times our delta T. And our next step is we combine like terms, or we distribute it into the equations, the parentheses. We get 564.84 delta T equals negative 1,569 delta, final temperature, plus 94,921.362. It's a big number. And then we combine like terms, we get on the same side. So we have 2,133.84 final temperature equals 94,921.362. And then we just divide both sides by 2,133.84. And we get a final temperature to be 44.48 degrees Celsius. So that will be the temperature when the coffee and the ice, the melted ice, reach thermal equilibrium. So there's an overview of what we've discussed today. First thing we did is we brought the ice up to the melting point, up to 0 degrees Celsius. Then we melted it, and then we took that energy, how much energy it took to melt the ice, and took the energy away from the 90 degrees Celsius coffee to get our initial temperature of the coffee, and then we subtracted, and then we find the final temperature of the thermal equilibrium.